Hello Godoniers! Shaders are a very powerful tool that can be used to create interesting effects for your game. Unfortunately, they're also a bit intimidating to get into. So we're going to learn the basics of how shaders work, and we're going to explore how you can create your own shaders in Godot. This is a beginner to intermediate level tutorial. You should know how to use the Godot editor, and you should know at least the basics of either GDScript or C#, as this will help you a lot when learning the shader programming language. We'll also use visual shaders, so if you don't know a programming language yet, you should still be able to follow along. We'll also need to use quite a bit of math, so it will really help if you're comfortable with basic math and maybe functions and vectors. But if you aren't, don't worry, we'll keep things simple and explain them as we go. So, what are shaders? Shaders are programs that run on your graphics card rather than on your CPU. They can change how meshes and textures are getting rendered. Everything that you can see in Godot is actually a mesh. Even 2D stuff like a sprite or text is still a mesh under the hood. Right here, we have some sprite 2D, a label with text, and a polygon 2D. And I've created a second scene where I added a wireframe shader to these, so we can see the mesh that is used to render them. A mesh has vertices and triangles. The vertices are these points that make up the mesh. The triangles are made by connecting the vertices. Now, in order to render a mesh, the graphics card will need to do a bit of work, and part of this work is to run a series of shaders. We start with the mesh, which defines the geometry of the thing that we want to render. Here we just have a simple sprite. Now the graphics card will run the first shader, which is the vertex shader. This shader will run for each vertex of the mesh, and it allows us to modify the vertex data. For example, we can change the position of the vertex. Here, the vertex shader is moving vertices of the sprite to give it a swaying motion. It's important to note that a vertex shader can only modify the vertex data. It cannot add or remove vertices or triangles. After our vertex shader has run, the graphics card now knows how the mesh is finally going to look. And the next step is to rasterize the mesh. Rasterization surely sounds a bit intimidating, so let's have a look at what it actually means. Rasterization means that we put a grid on our image and then look at what is inside of every grid cell. This is very similar to taking a picture with your smartphone camera. Here we have a real-life cat holding very still so we can take a nice photo of it. Thanks, buddy. So, let's point our smartphone camera at the cat. The camera has a sensor, and the sensor has a grid of sensor cells. Now each sensor cell will measure the amount of light that hits it, and will then produce a packet of data that we call a pixel. These pixels will make up our final image. Now the graphics card will do a similar thing with our mesh. Here we have the mesh as it is after the vertex shader is done with it. Okay, so let's first have a look at the vertex shaders. I have a patch of grass here, and I want to make it wave in the wind like we just saw when we looked at the shader pipe. This is something I cannot really do with the transform settings. Well, I could try to rotate it a bit, but that looks odd. I could move it left and right, but that also looks odd, and the skew setting, well, it looks somewhat right, but it moves the bottom part of the grass, and I only want to move the top part of the grass. So I would need to modify the mesh of this sprite, which sounds exactly like the thing vertex shaders do. So let's create a shader then. We right click here, we select new, resource, and then we search for shader. And we have two options, a visual shader and a shader, which is the shader in the Godot shader language. We're going to start with the visual shader for now, and let's name it grass. Now we want to assign this shader to our grass sprite. And we can do this by going into the inspector. Then on the material, we drag our shader directly onto this material slot. Now we can double click the shader and we can edit it. The first thing that we need to do is to change the shader type up here to canvas item, because we want a 2D shader. Canvas items are 2D shaders. And then in the editor, we see that by default, we have the fragment shader part of our visual shader enabled, and we need to switch it to the vertex shader part. So what can we do here? There's a single node here named output that expects some output of our vertex shader. So, okay, we know where the output goes, but where is the input? Well, the input is not added directly to the shader graph, so we need to add it manually. We can right click anywhere in the shader graph, and then in this window that opens, we can add new nodes to the graph. We want to add an input node, so let's type input. It has a drop down, and in this drop down we can select what kind of input data we would like to have. Since we want to modify the position of the vertex, let's select vertex. The vertex position is a vector. A vector is basically a little package that contains a bunch of numbers. Well, this vertex position vector contains 2 numbers. You can see this by looking at the little icon here, which reads VC2, which means vector 2. So this is a vector that contains 2 numbers. Now we want to change this position so that the vertex moves. So maybe let's add another vector to the position and see what happens, right? So right click, search for add, and then we pick the add node, which has the VC2 icon, because we want to add 2 vector 2s. So now we can add something to our vertex position. To do this, we first drag the position into the A slot of the add node, and then we can type some numbers here into the B slot. Let's maybe say 50 to X and 25 to Y. Well, it doesn't seem to be happening a lot, but this is because we need to connect the output of our add node to the output node. So let's do this. And now we can see that the whole sprite has moved to the right and down. So that allows us to compare numbers. So maybe we can use the vertex coordinates to find out. So let's have a look at the sprite. And then let's see what coordinates are we actually getting here. The vertex coordinates are given in so-called local space, which means that they are relative to the sprite's center and they are in pixels. So our sprite is 256 times 256 pixels. And the center would then be at 128 pixels to the right and down from the top left corner. And this center gets the coordinates of 0.0, and then everything else is relative to this center. So when we know this, we can calculate the coordinates of all the 4 vertices relative to the center. And if we look at these coordinates, we can see that the upper vertices have something in common. Their y-coordinate is negative, while the y-coordinate of the lower vertices is positive. And we can use this to find out whether the vertex that we are currently working on is one of the upper vertices. Now, which node would we use for that? There is an if node that allows us to compare numbers, so maybe let's add one of these. So we right-click, we search for if, and we add it. So now the if node has 2 numbers, A and B. And the if node will return a vector 3 depending on whether A is equal to B, greater than B, or smaller than B. For each of these cases, we can configure what the output of the if node should be. So let's first plug the y-coordinate of the vertex into the A input, because we want to know if this is negative or positive. But how do we only get the y-coordinate of the position? Because we only have a vector 2 here. Well, we can click this little triangle here to get additional outputs that split this vector 2 into its components. They are somewhat confusingly named red and green, and this is because of some special convention in the shader language that allows us to use different names for the components of each vector. So X can also be named red, and Y can also be named green, and Z can also be named blue, and so on. But it's just different names for the same component, and we will see this later when we work with the shader language. So for now, we just need to know X is red and Y is green. So we get the green output, which is the y-coordinate, and put this into our if node on the A input. The B input we keep at 0 because we want to compare the y input with 0, and then we can set the output for A is less than B to be some value that we want to add to our vertex position, maybe 100.0.0. So our if node will now return a vector 3 with 100, 0, 0 if the y-coordinate of our vertex is less than 0, and it will return 0, 0, 0 in any other case. Okay, so we can now plug this into the add node. And we can see that only the upper vertices are moved, while the lower vertices stayed in place. When we look at the shader graph again, there's one odd thing. The add node expects a vector 2, but we plugged in a vector 3. So what happens with the third component? Well, in visual shaders, the editor will automatically convert between different vector sizes. In our case, we need a vector 2, but we got a vector 3 from our if node here, so the editor will just drop the last component. And if it's the other way around, then the editor will simply add a 0. When we look at the shader language later, we will have to do these conversions ourselves. So we were able to move only the upper vertices, but we would like to make it faster or slower. So zoom in a bit. And we can see that the grass is actually very slowly moving. So we right click and we search for vector 3, compose, and there it is. And we add it. So this has 3 inputs for x, y, and z coordinates, and it will return a new vector 3. So we plug the time into our x component, and then we plug this new vector 3 into our if node. Now the grass has moved, but it seems to stand still. Maybe let's zoom in a bit. And we can see that the grass is actually very slowly moving in larger numbers. So we need to is the sine function. It's forever as we put sine function with some number to make it sway more pixels. And we want to sway by 100 pixels left and right, so we multiply this output by 100. let's add a multiply node. Right click, search for multiply. And we need to check that the output of the sine function is a float. So we need to use this multiply with the float. So now we can plug the output of the sine function into this multiply node, and then we multiply by 100. And now the grass swings back and forth by 100 pixels. Well, that's great, but I think it's swinging a bit too fast, so I'd like to slow it down a bit. How can we do this? Well, what we can do is we can multiply the time with some number to make it faster or slower. So let's say we want to make the time go half as fast. We could multiply this with 0.5 or 1/2. So let's duplicate this multiply node here. You can press Ctrl D to duplicate. And then let's plug the time into the A slot and multiply it with 0.5. And the output goes into the sine function. Well, that seems to work pretty well. So now let's try if this also works for speeding up the animation. So let's maybe multiply the time with 2. Oh, we change it here to 2. And it does. Okay. Well, this is way too fast, so let's move it back to 1.0. But now we can make our grass sway, and we can also control the speed of this animation, which is great. So now that we have a functioning visual shader, let's see how we can write the same shader in Godot's shader programming language. Why would we want to do this? Well, there are a few reasons. First, visual shaders are somewhat limited. For example, we cannot use some programming constructs like loops in visual shaders, and we also cannot make our own custom functions. The second reason is that almost all shaders that you will find on the internet will be written in some shader programming language. So if you want to use these shaders as a basis for your own shaders, well, you will need to know how to read and write shader code. But if you already know how to write code in GDScript or C#, you will see that the shader programming language is actually not that different. So let's start by creating a new shader. So we right click on the file system, we select new resource, and then we search for shader. And this time we select the shader resource, not the visual shader one. We name it grass, and we also set the mode here to canvas item. And then we can attach this code-based shader to our second copy of the grass sprite. So again, we open the material slot and we drag the shader directly onto the material slot. Now we can open the shader by double-clicking it, and it will open a code editor down here. And we can see that currently there's not a lot going on. We have some instruction here that tells Godot that this is a shader for canvas items, so it's a 2D shader. And we have a function called fragment, which is currently empty. This function is actually for the fragment shader, which we will come to later. So for now, we can just rename it to vertex. And vertex is the function that is used for the vertex shader. If you come from C#, then this shader language will actually look very familiar. We have a return type of void. The function is named vertex, and it takes no parameters. If you're coming from GDScript, you will notice that a few things are a bit different. In the shader language, the return type is at the front of the function, while in GDScript, it is at the back. The shader language doesn't have the func keyword, so a function is simply identified by its name. Also, we use these curly braces here to mark the beginning and ending of code blocks, while in GDScript, we use indentation to mark code blocks. Finally, we have a comment here, which is created by writing 2 slashes, same as in C#. In GDScript, we would use a hash sign for this. If we look at the function, we can see that it takes no parameters and it also returns nothing. A return type of void means nothing, same as in C# and GDScript. So how can we get the vertex position and return a new vertex position to the graphics card when we have no parameters and return nothing? Well, in the shader language, there are a lot of built-in variables that are used for this purpose. We can go to the documentation here in the browser, and we see a list of all the built-in variables. And we can see that in order to get the current vertex position, we read a built-in variable named vertex. And if we want to write a new vertex position, well, we will just write to this same vertex variable. So now we know how to get data in and out of the shader. We can start to translate a new vertex. We read and we can see that in order to get the current vertex position, we read a built-in variable named vertex. And if we want to write a new vertex position, well, we will just write to this same vertex variable. So now we know how to get data in and out of the shader. We can start to translate our visual shader into code. So let's get back to Godot. Here's our visual shader again. So we can see which parts of the code correspond to which parts of the visual shader. And then let's begin on the left. There we have the current time, and the variable for this in the shader language is named time, all uppercase. Like in GDScript and C#, the shader language is case sensitive, so time lowercase is something different than time, all uppercase. Now we want to multiply this time by 0.5, so we can just type that in, time times 0.5. And the next step is to run the sine function. This also works very similar to C# and GDScript, so we just type the name of the function, sine, and then we give our slow time as a parameter in parentheses. Next, we want to multiply this by 100, so we type just that. Now, the compiler is unhappy about this. In the shader language, we cannot multiply floats with integer numbers like we can do in other programming languages. Our 100 is an integer, but the sine function returns a float. So we need to convert our 100 to a float before we can multiply. We can convert the 100 to a float by just adding a dot and a 0, like this. And now the compiler is a bit happier and we can continue. The next step is to make a vector where the x-coordinate is this expression that we have calculated so far. In the shader graph, we used a vector 3 for this because that is the only thing that the if node accepts. But actually, we only need a vector 2 because the vertex position only has two components, x and y, because we are in 2D. So we can create a vector 2 by calling the vec2 function. And then we pass in our x and y values as parameters to this vec2 function. So we type vec2, and the x value is this expression that we just made. And the y value will be 0, just like in our vector compose here. Now we need to do the if node. Like in GDScript and C#, there's a built-in if statement, so we can just use that. So we'll start with if, and then we need to give it a condition. And in the shader language, like in C#, this condition must always be in parentheses, like this. This is different from GDScript, where we can leave these parentheses out. Now let's have a look at the if node, and we can see that it compares the y-coordinate of the vertex with 0. And we can do the same thing here. We just take the vertex built-in variable, and then we write .y to get its y component. Remember that the y-coordinate was called green in the visual shader? We could also access this y-coordinate by typing G for green, as both are just different names for the same component. And this feature is very useful because in shaders, colors are usually stored in vector 4s. So you can type .x, .y, .z if the vector contains a position, and .r, .g, .b if the vector contains a color. And this can make your code a bit more readable. But in our case, we're going to use .y because we're dealing with a position here. Now we can check if the y position is less than 0. So we just type less than 0, and now our condition is finished, and we can close the parentheses. In GDScript, we would now indent the next line to start our if block, but in the shader language, we use these curly braces. We still indent the code, but this is just for readability. The compiler will still be happy if we don't do this. But it looks like the compiler is unhappy about our condition. We cannot compare ints with floats in the shader language, so we need to convert the 0 into a float as well, just like we did with the 100. Again, we can just add a dot and a 0 to the end of the number, and now it will be a float. Now, if this condition is true, we want to add this vector 2 that we calculated to the vertex position. So we write vertex plus equals, and then we add this expression. Now the compiler still seems to be unhappy, and this is because, like in C#, we need to end every statement with a semicolon. So we need to add a semicolon here, and now the compiler is happy. And we can immediately see the grass is moving. So just like with the visual shader, whenever we change our shader code, it will immediately update in the editor. And this is really nice because we don't need to start our game to see if our shader works. So you see, writing shaders in code is not really that hard once you know the differences of the shader language to the programming language that you already use. So should we only use code-based shaders then? Well, no. Visual shaders are really nice for learning how shaders work, and they're also really nice for prototyping. Now you can quickly try out a few different things, and you can see how they look without having to make the compiler happy all the time. And if you organize the graph well, it can actually be easier to see how the shader works when you come back to it later. Under the hood, the visual shaders are automatically converted into shader code, so there's no performance difference between visual shaders and code-based shaders. Our vertex shader experiment was quite successful, so let's have a look at the fragment shaders next. Fragment shaders allow us to change the fragments that the graphics card has produced when it rasterized the mesh. So we can change how things look before the graphics card will actually draw anything. As an example, we are going to make a shader that can replace a color. Such a shader is useful in a game where the player can select the color of their units. With the shader, you can just make one unit image and then replace the unit color on the fly in the game, so you don't have to make a lot of images with different color variations. I have prepared a sprite of a character, and now we want to replace the color of the shirt that this character is wearing. For this to work, the shirt needs to be in some color that is not used anywhere else in the image, so only the shirt's color gets replaced. And this is why the shirt has this nice green color. I have a second copy of this image here that we can use for comparison while we develop our shader. We will again start with the visual shader, so let's create one. We right-click, select New Resource, and then we search for Visual Shader, and we name it Color Replacement. And again, we drag it onto the material slot of our sprite. And then we can double-click it to open it up in the Visual Shader Editor. Again, we need to make sure that the shader type up here is set to Canvas Item because we are making a shader for 2D. This time, we stay in the fragment part of the shader. We can see that the output is a bit different from what we saw in the vertex shader. The most important output is the color that the fragment should get. We also have an output for alpha, which controls the transparency of the fragment. And there are a few other outputs, but we won't get into these for now. The input works exactly like in the vertex shader. So for getting an input, we need to add an input node. So let's right click and search for input and edit. And we can see that we have quite a few inputs. We want to select color to get the color that the graphics card assigned to the fragment when it rasterized the sprite. This is a vector 4, a vector with 4 components. The first 3 components are red, green, and blue. And the 4th component is the alpha channel, which controls the transparency. We can also click this little triangle like we did in the vertex shader, so we can get access to each element of the vector. Color values in shaders are always given in a range between 0 and 1. And this is different from how colors are usually represented in other areas, where red, green, and blue are given as a range between 0 and 255. For example, let's have a look at the color of the shirt of this character. I have a little color picker here, and we can use this to pick the color of the shirt. Now we can see that the shirt's color is 0 red, 255 green, and 0 blue. But in a shader, we need to give these colors as a value between 0 and 1. So if we want to know how this color would be expressed in the shader, we can use the raw tab of our color picker. So let's open the color picker again, and then select raw, and then we can pick. And the color picker will automatically convert the color that we pick to a range between 0 and 1. So now we can see that the shirt's color is 0 red, 1 green, and 0 blue. So how can we use this knowledge in our shader? Well, the shirt is the only part in this image where the green part of the color is 1. So we could try to use the if node again, that we already know from the vertex shader, to check if the green channel is 1, and then replace the input color with some other color. So let's try that. We right click, search for if, and then we edit. And then we plug the green into our A slot. Now we check if the green channel is exactly 1, so we put a 1 into the B slot. And then let's say when A equals B, we want to make the shirt blue. Blue would be 001, so we type 001 into the A equals B slot. And in all other cases, we just want to have the original color. So we plug the original color into the other two slots for A is greater than B and A is less than B. And now we can plug the output into our output node. Now everything is connected, but the shirt is still green. So what's going on here? Well, the problem is that we are comparing two float numbers here. And there's always some potential rounding error when we compare two floating point numbers and want to know if they are equal. This is the reason why this node has a tolerance setting. When we increase this tolerance, then the node will still treat A and B as equal, even if they are a tiny bit different. So let's try to set the tolerance to something small, maybe 0.001. And now the shirt is actually turning blue. But we get this really ugly seam here where the shirt still remains green. So let's find out why we get this. I'm going to set the filtering on the second sprite that we have here to nearest, so we can see the original pixels of the sprite without any interpolation. Now let's inspect the colors of the seam of this shirt. It looks like that they are actually in different shades of green. Some are a bit darker, so the pixels blend more nicely together with this black border. Let's verify this maybe with our color picker. So we can see that the red and blue parts of the colors at the seam are still 0. But the green part falls below 1, where the shirt color is blended into this black border. So maybe we could try to increase the tolerance setting of our if node, so it will also affect parts where the green value is a bit further away from 1. Well, let's try this out. So we increase the tolerance slowly and then see what happens to our seam. So this makes the seam smaller, but it also does some things that we don't want. First, we can now see that the shader affects the whole sprite, not just the shirt. And we also see that our replacement color is always a solid blue and doesn't nicely blend with the black border like the original green did. So this solution with the if node clearly doesn't work. So let's take a step back and think about how we could solve this problem in a different way. Maybe we can split the image into two parts. One part that is the shirt and another part that is everything but the shirt. Then we could apply the color change only to the part which has the shirt and leave the rest untouched. And in the end, we just combine our two parts back into one image. So how can we find out which parts are the shirt and which parts aren't? Let's use our color picker again to see if we can find a way to distinguish them. We can see that everywhere where the shirt is, red and blue are 0, and green is some value between 0 and 1. On the other parts, red and blue are above 0. So we know that if red or blue are above 0, then it's not the shirt. Which node could help us to check if red or blue are above 0? The if node we have used only allows us to compare a single number, but maybe there is another node that we could use. Let's have a look at the list to see if we can find the variant of this if node that can help us. So we right click and then let's search for if again. So it looks like there is only this one if node that we already know. So we will need to use a bit of math to massage the data that we have into some form that is a bit more helpful to us. What we need is some node or mathematical function that can take a color and then gives us a number back that tells us how much red and blue is in this color. There is no built-in node that can do this for us, so we will need to build something like this ourselves. So let's break down the problem a bit. As a first step, it is probably a good idea to strip out the green part of the color from our color vector so it doesn't get in the way when we want to calculate how much red and blue are in the color. So let's add a multiply node. We right click, search for multiply, and we pick this vector 3 multiply node here because we want to multiply two vector 3s. Now we plug the input color into A and we multiply this input color with 1, 0, 1. Vectors are multiplied element by element. So when we do this multiplication, red gets multiplied by 1 and stays as it is. Green gets multiplied by 0 and will be 0. And blue gets multiplied by 1 and stays as it is. Let's plug this multiply node into the output node and see how that looks. We see that the green color is completely removed from the picture. Everything that was green, like the shirt, is now black, and everything else has its green part removed, so the picture now has this purple tint to it. So after our multiplication, our vector only contains the red and the blue components. And now we can use a built-in function to get a number that indicates how much red and blue are in this color. And this built-in function is the length function. So let's add it to our shader graph. We right-click, search for length, and then we add it. And now we plug this vector into the length node. And the length node will now calculate the length of this vector. So what is the length of a vector? To understand this, let's have a look at some vectors. I have prepared a little graph here. And here we have a 3D diagram with X, Y, and Z axes. We follow the conventions of shaderland, so X is red, Y is green, and Z is blue. And at the bottom here, we have a vector where red is 1 and green and blue are 0. The length of this vector is just the distance from the origin at 0, 0, 0 to the tip of this vector. And just by looking at it, we can see that this length is 1. Now let's maybe look at a vector which only has blue in it. This would look like this. Red and green are 0 and blue is 1. And this vector also has a length of 1, just on a different axis. Now how would a vector look like when we mix a bit of red and a bit of blue? Well, let's have a look. Here we have a 0.3 red and 0.5 blue vector. This would give us some darker purple color. And we can also see that this vector is much shorter than the other ones because we have a lot less red and blue in it. If we would change that color to a bright purple where the red and blue are 1, we get a much longer vector. So we can see that the length of the vector is a good indicator of how much red and blue are in the color. So let's get back to our shader. We can drag the output of the length node into our output node and we get some grayscale image. This is because the single number that the length node returns is used for all three color channels, red, green, and blue. And if red, green, and blue are the same number, then we get some shades of gray. So now we can see that every part of the sprite that has red or blue parts in it is some shade of gray, while all the other parts that have no red or blue in them, like the shirt and the black borders, are black. What we have made here is called a mask. A mask is a black and white image that we can use to control which parts of an image are visible and which parts are not. If you have worked with image editing programs like Photoshop or Affinity, you may have seen masks there as well. So we have this mask from our length node, but how does this help us to separate the image? Well, remember how we removed the green part from our color by multiplying it with 0? We can do the same thing with our mask. Let's try this out and duplicate this multiply node here. We can press Ctrl D to duplicate. And then let's drag the mask into the A input and the original color into B. Now we can connect the result to our output and see what happens. So the mask sort of works. The areas where the mask was black are fully black, so that part worked nicely. But the other areas are somewhat darkened and don't keep their original color. But what we want is that the areas where there is any amount of red or blue keep their original color, and everything else just becomes black. So how can we do this? Well, let's look back at what the length node produces. I've made a little visualization for this here. So this is the output of the length node that we just saw. But if I move the camera, we can actually see the calculated length in 3D. And there we can see that for areas where there is less red and blue, we get less length. And if we multiply this with the original color, then the original color will get darker in these areas, because if we multiply a color with a value smaller than 1, it will get darker. But we are really only interested in whether or not there is red and blue in the image. We don't really care how much red or blue is in there. So how could we change this into a mask that is black, where we have no red and blue values, but is white everywhere else, like this? Well, there's a built-in function that can help us with this. It's called step. So let's get back to our shader and add a step node. This step node has two inputs. One is called edge and the other is called x. To understand what this node does, let's have another look at the step function here in the browser. So this is the step function. I have set the edge parameter of this step function to 0.1. So now let's see what happens when we plug the length that we calculated into the step function. This part here is the shirt, and it's fully black, so the length is 0. And if we plug this into our step function, we get a 0, because our 0 input is less than the edge. And for this part here, the length is about 0.3, so if we plug 0.3 into the step function returns 1, because 0.3 is greater than our edge of 0.1. So we can use a step function with a very small edge to decide if the amount of red and blue is greater than 0 or not. So we plug the length of the vector into the x, and we set edge to 0.01. And now let's plug the result of the step function into the output to see what happens. And we can see that our mask is now either black or white, but we have no more shades of gray in it. Now we can again try to multiply this mask with our input color. And what we get back is one separated image with the parts that we don't want to change. Now that is great, but how do we get the parts that we do want to change? Well, we can just invert this mask, and we can do this with a 1 minus node. So let's add a 1 minus node, right click, search for 1 minus, and we add it. So the 1 minus node just subtracts its input from 1. So you take the number 1, you subtract the input, and the result is the output. If we put in white, we get black, and if we put in black, we get white. And this is exactly what we want. So let's check what happens if we multiply our input color with this inverted mask. So let's duplicate this multiply node here. And then we plug the original color and the mask into the multiply node, and then connect this to the output. And we see that we get just a shirt while everything else is black. Okay, so now we have separated our image and we can now start to recolor only this shirt part. But how would we do this? Well, we could start by just multiplying our shirt mask with the replacement color. So everywhere where the shirt mask is 1, we get the replacement color, and everywhere else we get black. We don't have a replacement color yet, so let's add a color constant node. And now we can pick some color. Maybe this blue here. And now we can multiply this mask with our replacement color. Well, it's blue all right, but it does not only affect the shirt, but also the borders and some other parts of the image. Also, there is no blending with the border. Every fragment gets the exact same shade of blue. So the mask alone is not enough. It only tells us where we need to apply the replacement color, but not how much of it. So what would be a good indicator of how much of the replacement color we need? Well, you may have guessed it. It's the green channel in the original image. The more green we have, the more of the replacement color we want, but only in the areas of this mask. So we can use this green channel to refine our mask. Let's try this. We can get the original green channel from our input node. This is a float number. The mask is also a float number. So this time we need a node that multiplies two floats. So let's right click, search for multiply, and then we pick this one that multiplies floats. And now we can plug the green channel and our mask into it and then check the result. And boom, we have a really nice refined mask that only selects the shirt and also nicely blends with the black border. So now we can again try to multiply this refined mask with our replacement color. So let's plug it in. And we get a nicely replaced shirt color. Great. So now we have the two parts of our final image that we wanted to have. We have the shirt with the replaced color, which has all black around it. And we have the unchanged part, which is black, where the replaced shirt should go. Now we want to combine these two back into a single image. And to do this, we can simply add them together. Why does this work? Well, because everything that is black is all zeros. So when we add the two images together, the black parts will be 0 plus whatever color is in the other image. So let's duplicate one multiply node and change it to an add node. And now we can drag the outputs of our two multiply nodes into this new add node, connect that to the output, and voila, we have a nicely replaced shirt without any seams. That's great, but we're not fully done yet. In our game, we want the player to be able to select a color for their character. So we need to be able to change the replacement color from our game code. Right now, it is hard-coded in the shader. So we need a way of sending data into our shader, and we can do this with a shader parameter. So let's right-click and search for parameter. And we want to give the shader a color as a parameter, so we use a color parameter node. We can give this parameter a name. Maybe let's call it replacement_color. And then we connect this to this multiply node where we had the hard-coded color. Now we can go to our sprite in the material section. And here we have a new shader parameter where we can set the replacement color. But we want to set this parameter from our game code. And this is where our color picker here comes in. We want to select a color with this color picker, and then in our game, this should update the color of the shirt. So let's add a script to our sprite. And let's name it color replacement.gd. And now when the player changes the color of this color picker, we want to be notified in our script. Notification sounds a bit like using signals, so let's check the signals that the color picker provides. In the signal list, we can see that the color picker has a color change signal. So let's connect this to our replacement script and create a new function on color picker color changed. Inside of this function, we want to change the replacement color of our shader. To do this, we first need to get the material of the sprite, as the shader is part of the material, like we can see in the inspector. Luckily, the material is available as a property, so we can just type material. The material has a function called setShaderParameter, which allows us to change the value of a shader parameter. And as the first argument, the function expects the name of the shader parameter that we want to change. We named our shader parameter replacement_color, so we type replacement_color. Now we need to give the function the new value that we want to set, which is the color that our player just picked. Luckily enough, this is given to us as part of the color change signal up here, so we can just give this into our function. And now we can run this and see if it works. So let's select a nice color for the shirt, maybe a neat red. And this seems to work out nicely. Before we wrap it up, let's translate our color replacement shader into code so we can see how to write a fragment shader using the shader language. So we create a new code-based shader, right-click, new, resource, search for shader, and we create a shader. And let's name it color replacement, like the visual shader that we created. And we assign this to the second sprite here. Now we can start editing, and the shader type is already set correctly to canvas item. We also have an empty fragment function already generated for us. So let's look at our visual shader and start translating. We first multiply the input color with 101, so we can strip out the green channel. Input and output in fragment shaders work exactly the same way as in vertex shaders, so we read and write predefined variables. So let's add this to our code. So we write vec3 color without green. The predefined variable for color is named color, all uppercase. So let's multiply color with vector3 101. We see that the compiler is again unhappy about this, and this is because the color variable is a vector 4, and we cannot multiply a vector 4 with a vector 3. In the visual shader, this was not a problem because the visual shader editor automatically converted the vector 4 to a vector 3 for us, but in code, we need to do this ourselves. So we need to make a new vector 3 which only has the red, green, and blue components of the color vector. So we create a new vector 3 by calling the vec3 function, and then we give color.r, color.g, and color.b as arguments. And then we can multiply this with our 101 vector. The compiler is now happy, but this is really a lot to write. When programming shaders, we very often need to extract information from vectors and put this information into new vectors of a different size. To help with this, the shader language has a built-in feature called swizzles. So to create a vector 3 with only the red, green, and blue components of the color input vector, we can just write color.rgb. And this .rgb is called a swizzle. So this is a super helpful shorthand notation to extract information from some vector. Next, we want to calculate the length of this vector to find out how much red and blue are in the current fragment. The shader language has a built-in function for this, and it's called length. So we can write float amount of red and blue, and this is the length of color without green. The next step is to use the step function to create a mask. Let's also make a variable for this, maybe red and blue mask. Step function is also built in, so we can just write step. And as a first parameter, we give the edge, which is 0.01, like in our visual shader. For the second parameter, we need to use the length of the vector, which we called amount of red and blue. So we copy that in. So now we have our mask that masks everything that has red or blue components. Let's quickly try this out to see if we're still on track. We can output the mask by writing it back to the color variable. So let's write color equals red and blue mask. Unfortunately, the compiler is again unhappy about this. This is because the color is a vector 4 and we are trying to write a float to it. What we actually want is to write this float into the red, green, and blue components of the color. So let's try if we can use a swizzle for this. So we change color to color.rgb. Seems like the compiler is still unhappy because now we have a vector 3 on the left and a float on the right side. So it looks like we need to build up a vector 3 with the red and blue mask in all 3 components ourselves. We write vector 3 and then we put red and blue mask for each component of the vector 3. And now we can see in the output that our mask is actually working. Creating this vector 3 down here is a lot to write, but luckily there's a shortcut for this as well. If we want to make a vector 3 where all 3 components are the same, we can just write vector 3 red and blue mask. Okay, so now back to converting our shader. Here, our processing splits into 2 parts. In the upper part, we multiply the mask with the input color, and what we get is the part of the image that we don't want to change. So let's do the multiplication and add a variable named retained color to store the result. Now for the lower part. Here we use a 1- node to invert our mask. In the shader language, we don't need a special 1- function. We can simply subtract the red and blue mask from 1.0 to invert it. So let's make a variable called green mask and then subtract the red and blue mask from 1.0. Now we want to make a refined mask by multiplying this green mask with the green channel of our input color, so we get the nice blending. We can just add this to our green mask calculation, so there's no need to make a new variable. Let's again output this so we can see if we're still on the right track. We can move this line down here and just change the output to the green mask. This doesn't look right. We should only have the shirt visible.
Hi everyone! If you watched the video about the simple transition... Hi everyone! As you may have noticed, I recently released a new ebook that practically... Hi everyone! If you watched the video about the
Good morning, afternoon, or evening, wherever and whenever you are. My name is Ben, and welcome to this Godot shaders tutorial for absolute beginners. In this video, I'm going to cover the basics of shaders in Godot. Actually, just the very basics of a fragment shader. So we're going to have a new project here in Godot and drag over our Godot icon here. And I'm just going to set the transform to 0, 0. In order to apply a shader, you're going to need some sort of canvas item. In this case, I'm going to use a sprite that we can apply our shader to. Now we'll save this scene as icon.
Welcome to Sector 12B. Sector 12B. To Sector 12. All visitors must comply with 12B ordinances. Failure to comply will result in immediate apprehension and containment. Your visitation microchip is now activated and expires in 72 hours. Visitors must report back to the sector gateway within that time. Please respect the citizens of 12B and enjoy your stay. visitation microchip is now activated. Visitation microchip is now activated. Your visitation microchip is now activated. Visitation microchip is now activated.
Even without the damage to the brain, the creature has the mind of a murderer.
commodity I know of is information. Wouldn't you agree? Illusion has become real, and the more real it becomes, the more desperate they want it. Capitalism at its finest. It's not a question of enough, pal. It's a zero-sum game. Somebody wins, somebody loses.
So if you need me, won't you call me tonight? If you're in trouble and you need me tonight, just call. onyx, heart of the light. I am onyx, black and white. Save me from this paradigm. Save me from the end of time. Enemies raging behind my eyes. Shadows caress me while whispering.
Behind this strange signal, there's an alien intelligence that knows all. This is the airlock chamber to bridge.
Seems almost a message coming from space.
The unknown space.
Come on, relax. You know that thing must be 100 years old. beyond known space. Come on, relax. You know that thing must be 100 years old. Beyond known space.
Don't tell me you don't tell me you are where you told me to be. Just write down where you are. Can you do that for me?
The unknown space.
shells of what once used to be. On cobalt streets, temptation sparks like electricity.